My name is Saša Jurić, and I come from a small startup company called Apple. And we are doing some very interesting stuff with data organization and privacy. And unfortunately, I don't have time to discuss this in detail, but I wanted to mention it now. We're using Erlang a lot, and maybe if you're interested, you want to check us out at erlang.com. There should be somewhere on those pages a high-level white paper available on how we approach the subject. This is going to be an introductory talk aimed at people into Elixir and Erlang. Fairly lightweight stuff, high level. I really want to provide some reasons which are personally quite important and relevant for considering Erlang in many cases as a development platform of choice. And I also want to demystify this thing to some extent, make it seem less of a mention of black box and more of a thing that you understand what exactly does it do to support your cause. And I will not be focusing on any particular language. I will be more oriented towards some foundational stuff that we get from our VM. And this is where I personally find the biggest benefits, the most compelling reasons for choosing any of those languages, which are definitely in their own right very interesting, that brings some nice things to the table. But I really think it's the VM that makes this whole ecosystem stand apart and be very different and be unique compared to anything else that's available today. So that's what I'll focus on. And I will somewhat incorrectly use the term Erlang, any language plus VM plus of course the OTP framework. Now the challenge I'll discuss them very vaguely broadly. We describe the property of the system to provide most of the service most of the time. Preferably all of the service all the time. We can allow some downtime, but as little as possible, hopefully none. And to do this for some longer period of time, possibly even forever. And in my opinion, this is a very important property. I don't think it's an option anymore these days for many kinds of systems, if it ever was. Because essentially, if the system is not highly available, it means it is frequently failing. And presumably, we don't want to have that property in our system, because ultimately they are used by some real people, by some end users. And those users may become annoyed if things start to fail frequently, and they may look for alternatives, they may move someplace else, and ultimately we may even end up being out of business. And I really don't think anyone of us wants to be in that place. So I really don't think it's a niche thing, it's something reserved for some special domains. I also don't think it's a scale thing. You don't need to be like super huge, have zillions of users. You don't need to be Ericsson or WhatsApp or something of the sort to have this requirement. It also doesn't come easy, doesn't come by chance in my opinion, because essentially a software system is a complex thing. Think powered by many different components. There may be multiple machines involved. We may be using some third-party services, maybe external data sources, payment gateways, whatnot. And because we have many collaborators there in the system, there are increasing chances something will go wrong at some point. It's illusionary to believe that everything will always work perfectly, and we kind of have to let go of this illusion and architect our systems around the fact, make them more resilient to any kind of failure. And this requires some effort, right? Some work, so it's worth considering some tools that may help us in the process. And Erlang is one such tool. It's the hammer of a particular nail, and it's the challenge it has been solving in production for more than 2 decades now, I believe, in all kinds of systems, large and diverse, and it's really proving itself in production dealing with this challenge, and as such, I think it should be seriously considered as a development platform of choice. For me personally, as a backend-side developer these days, Erlang is practically the default choice for anything on the server side. With the rationale that on the server side, high availability is almost always required. That is not an easy problem, as Erlang has a proven track record, and it's one of the few, if not the only development platform built with this particular challenge in mind. And I would choose it personally, by default at least, because I believe it's the tool that is helping me the most in one of the harder areas I would have to face no matter what kind of thing. That's kind of my personal position. And I want to make it clear, and this is possibly the most important point of this talk, that this doesn't happen by magic. Right? Just because we're writing our stuff in Elixir or Erlang will not make it magically available or reliable. Erlang does not do that for you, and I really don't think anyone else can. Because essentially your system is your own story. It's very unique, different from anything else out there. In the way it's built, in the way there are multiple components that codepend to provide total service. And what exactly should happen when individual pieces start to fail is your decision. You need to make this call on a case-by-case basis, and no one else can do that but you. So what you can expect to get from Erlang are some kind of low-level foundation, very simple building blocks with very strong guarantees, practically no gotchas there, and you somehow use those things to work your way gradually toward a more reliable system. It's kind of the way I see it, And in the process, I think you should aim for a couple of higher level technical properties. So the system should definitely be resilient to any kind of failures, right? It should mitigate failures. No matter what goes wrong, the attack should be as minimal as possible. So we can provide most of our service without interruptions. It should be able to self-heal, to recover from failure automatically as soon as possible, and thus resume the full service. We need scalability so we can address the load shell. Hopefully our system will become popular in time, right? Users clock in, we have more work to do, we reach the limits of our hardware, and then we add more hardware, and the system knows how to use it automatically. And it goes without saying that the system should provide responses in a timely manner, whatever that means for your particular use case. But obviously, if it takes like days or months to get a response, the system is practically not working. And this is especially important in some critical times, like time to complete failures or increased load. If somehow, under some conditions, seconds turn to minutes, for example, then the system becomes unusable. Presumably, we want to avoid it. So we can somehow get all of this in Erlang systematically by relying heavily on its concurrency. This is kind of like a magical ingredient. And in my opinion, concurrency in Erlang is really synonymous to total separation, runtime separation to be precise. So two concurrent things are two separate, distinct runtime entities. Now, a concurrent thing in Erlang is called a process, no relation to code process or thread, much cheaper, lighter thing. And it's a computational thing, it's a sequence of expressions, and of course the processes have their own separate execution paths. They share nothing, they have separate stacks, heaps, no shared memory. They're really like two distinct runtime entities. Now, of course, being a part of the same system, some of them will need to cooperate, collaborate, and for this purpose, we can use messages. They can send themselves messages, where a message is essentially just a piece of data, whatever you can store into a variable, right, arbitrarily simple or complex. And when we're sending it, we're really sending a snapshot of it, a copy. Right? This copy, because data sharing is not allowed, this copy is placed in the mailbox of the receiver, and the sender then moves on, doing its own stuff. The receiver is not interrupted in any way. It will take the message when it pleases, and at the time it will pull one message and do something about it. This is a very simple but very powerful and very important collaboration and communication. Right? Now, on top of this, we frequently build so-called server processes. And this is where Erlang is set to resemble the actor model. So a server process is a vanilla process implemented in a special way, and usually you don't need to do this yourself. There are frameworks available, most notably a thing called Server, a framework. But the gist of it is a server process runs for some longer period of time, and it maintains its state. Again, arbitrary data, which is of course internal and private to this process, and it runs a loop. Now in the loop, it waits for one message to arrive, and when it arrives, it handles it. It does something with the message. Right? Based on the message content and the current state, it may run some computations, it may talk to other processes in the system, it may create additional processes, and it may send a response message back to the caller process, and it will compute the new state. Right? Based on the current state and the message, we get the new state, it loops with this state, and then repeats the operation. So you can think of it kind of like a single-threaded server, right? Handle one message at a time. And those messages are literally requests that other processes can use to interact with it, to make it do something. So we could, for example, have a server process responsible for a single bank account, and in the simplest implementation, the state here would be number, right, the money that we hopefully have. Then we have many different clients, themselves processes. They can use messages to interact with it, to manipulate or query this particular bank account. And they may send their messages at the same point in time, and yet those messages will be handled one by one in the order of arrival. And this is how we synchronize competing actions. This is how a process can protect the integrity and consistency of its state. And we don't need semaphores, mutexes, locks, and stuff like that to do this, right? So it's a way simpler approach to concurrency, in my opinion. For me personally, concurrency becomes less something I'm afraid of and more something that I'm inclined to use in many cases where applicable and where I can get some benefits. And it's also a cheap thing. This Erlang process is way cheaper than heavyweight processors or threads. In terms of memory overhead, when you start it by default on a 64-bit VM, it will take up about 2 kilobytes for stack and heap, and then of course it may grow if it needs more. And you can really create those things in abundance, like in billions if needed. And we rely on this, we use this property. Because concurrency is cheap and because it's easy, in Erlang we use it a lot.
we write highly concurrent systems. It is possible that, I don't know, a smaller system can easily be powered by a few hundreds or maybe a few thousand of processes, while medium to large system might reach for tens or hundreds of thousands or sometimes even millions of processes. And the general idea, very broadly speaking, is whatever can be labeled as a distinct activity in a system should probably be implemented by at least one dedicated process. Usually there's opportunity to subdivide even further. Right, so this is kind of like a generic diagram. I will provide a more concrete example in the last part of the talk. But the idea is that we use a lot of concurrency, and due to the way it works, due to some of its benefits and some of the supporting tools, we can get some nice benefits in our systems. Right, so first of all, because everything is separated, this is so-called share nothing concurrency. A failure of one thing does not disturb anyone else in the system. Right, the process fails, everyone else keeps running. And a failing thing could not leave any garbage, any corrupted data behind. So we have like 1,000 processes running, one of them fails, you have 999 processes running and providing the most of your service. This is the isolation part, right? Now, obviously being a part of the system, those survivors may need to depend on the failing thing, so we want to bring it back up as soon as possible. And this is possible because the crash is not abrupt, but it's also not silent. Anyone can be notified about the process termination. Any process can ask from a VM to get a message if some particular process terminates. So as a process, I can say to my VM, hello, this is me, please let me know when process foo dies. And if that happens, I get a message, foo has terminated with a reason bar, and then I handle this message, I can do something about it. This is what I like to call a failure propagation through a concurrent system, right? So we have like one thing fails, someone else can get that information and do something about it. And there are all kinds of interesting patterns here, but possibly, arguably, the most important one is supervisor, which really builds on top of this foundational stuff. It's implemented in plain Erlang as part of the OTP framework, and it kind of relies on this simpler stuff. So supervisor is a process. It is, in fact, a server process, which we can use to start, supervise, and monitor worker processes, which are the bread and butter of our system. This is where the action is happening, and we are providing some useful value, providing some service, right? So I can tell to my supervisor, please start me these workers with those arguments, and it does that. And it also wants to be notified when any of those processes terminates. And if that happens, it gets a message. It handles the message by starting the new worker with the same set of arguments. And the new worker, of course, starts with a clean, fresh, and stable state, does not inherit any corrupted garbage from the failed one. Now, a supervisor can supervise multiple children, not all of which need to be workers, and this is how we build so-called supervision trees, where usually leaves should be workers, and nodes, non-terminal nodes, should be supervisors. And there are all kinds of interesting options there, but I'll just discuss the most basic case. So let's assume that a single worker somehow crashes due to some exception, it terminates. Parent supervisor gets the message and it handles it by starting the new worker, right? And if that works, then great. What we experienced, we had a single failure, everything else runs without any interruptions. We recover from a failure automatically and concurrently to everything else. So that's kind of like the best case scenario. Now sometimes, of course, restart may not necessarily help. And we will end up in a restart loop, right? The worker fails, we restart it, it fails again, we restart it again, and so on and so forth. And at some point, supervisor will give up, right? When some configurable threshold is exceeded, we have too many restarts per time period, then supervisor gives up, terminates its complete subtree, all of its descendants, together with itself, and it essentially escalates the restart procedure one level above to the parent supervisor. So what's kind of happening here is we are trying to recover from a failure at a very local scope, very narrow scope, and if it doesn't work, we are moving wider, wider, wider until we are able to find some area of the system that needs to be restarted to resume the full service. And the rationale that this should work is because the system was originally working, right? We started it, it was providing some service for some time, and presumably now it's failing because there is some corruption in the state of single worker or maybe of some workers, and we are trying to find the minimal possible surface that needs to be restarted so we can restore the full service. And somewhat magically, but it's actually quite logical because this supervision tree is kind of established in an orthogonal way to the main code. The main code of those workers is in many ways liberated from error handling constructs, paranoid try catches and whatnot. It usually follows the happy path, describes its intention. We even frequently use pattern matching to assert our expectations and fail fast if those expectations are not met. And then we rely on the supervisors as a safety net to recover us from some unexpected situations. Now, because the system is highly concurrent, there's a lot of potential to be more efficient, to run it more efficiently. And this is where VM steps in. It does its magic, right? So when we start the VM, it's a single OS process, and it uses only a handful of OS threads to do the job. The most important of those threads are schedulers. We have by default one scheduler per CPU core, and there, of course, schedulers are in charge of running our processes. And they do frequent context switches. No matter what your process does, like be it CPU bound, IO bound, or some combination, you can be pretty sure that it will be frequently switched out. And this is a good thing because it prevents a single process to paralyze your entire system or some significant part of it for some longer period of time, right? So the way it works is when a process gets the slot in the scheduler, if it's waiting for a message and the message is not there, it's suspended and someone else gets the slot. If it is doing an I/O operation, then this will in fact be performed on a separate thread, so-called async thread. I believe we have 10 of those by default. And in the meantime, the scheduler can do something else, run some other processes, right? And of course, long-running CPU-bound process will be preempted very quickly. You can expect this to happen in a sub-millisecond time. So there are a lot of those switches. I should also mention that garbage collection is not done on a system level. We don't have a global system GC pause. We have this what I like to call micro GC per process, which is possible because we have nothing share concurrency. So when a process has the slot in the scheduler, if it needs more memory, if it needs to expand its heap, then during this expansion there will be this micro GC, and it's perfectly possible that you have a single scheduler doing this micro GC thing, while all others are in fact providing some useful service and doing something meaningful. And all of this makes your system more predictable in their nature, right? You fine tune it, you get some latency, and you can expect less variances, less deviation in your response times. And of course, it's obvious that VM goes to great lengths to make efficient usage of all the resources. It uses hardware as much as possible, and you can also scale up, right? If you reach limits of your current hardware, you can put the system on a bigger, better, stronger machine, and it will just spread itself over all available cores. The final piece of the puzzle is the support for distributed systems. So it's possible to connect multiple VM instances in a fully connected cluster. And this improves our scalability and fault tolerance because now we can scale out, right? We can stack multiple machines to support the total load and add additional machines to accommodate the extra load. And also it improves our fault tolerance because we can now tolerate crashes of the entire machine, right? And survive them and provide our service. Now, even though you don't necessarily plan for it, in many ways your highly concurrent systems in Erlang will already be distributed. Because what we're essentially doing is, by being highly concurrent, we are distributing a huge workload over a large number of, of separate entities, which are processes. And those things, of course, communicate via messages. And we use the same primitive regardless of the locality of the target, right? The receiver can be in the same VM instance or it can be on another machine. We use the same thing. So in many ways, our systems are already down the road to being fully distributed. This is not going to be an easy task. I will not lie to you. There are some inherent challenges with distributed systems, no matter what you do or how you do it, most notably dealing with network partitions. But you get some boilerplate already available. You have support from third-party libraries. And of course, you should reach for stuff like React Core, for example, from React that can simplify your life. So yeah, that's the general idea. A lot of concurrency, share nothing semantics, some supporting tools from VM, and a lot of effort by the VM itself. And then we can get some nice stuff, which in my opinion ultimately makes our system more available, right, providing service. So what does it mean to be highly concurrent, right? This is kind of the last part of this talk where I'll try to provide some example, an adapted example inspired by the feature I have built for my previous former employer. And it is for this particular feature that I originally reached for Erlang some 5 years ago. And this feature is in many ways powered by Erlang and to some extent also even by Elixir. Now the feature is so-called live betting. It works in the online betting domain and it allows end users, so-called players, to visit the online betting site and place bets on matches which are currently in play. Now, because we are dealing with something that is happening right now, obviously we are dealing with a continuously changing stream of information that we have to constantly transmit to connected users, a couple of thousand of them simultaneously at peak time. And we have to do this in near real time, right? We cannot afford significant delays between what we're showing there and what's really happening. And the changes are happening fairly frequently. This is not obvious here because this is like a partial screenshot. At peak times, we have about 50 simultaneous matches. This central area, it goes wider to the right. And those numbers that you probably don't see very well in the central area are so-called betting odds or coefficients. And they determine the amount of money a player may win in the case of a successful bet. And we generate a lot of those odds per single match, especially for some more dynamic sports such as basketball or tennis, where things tend to change pretty frequently. Now, a high-level overview of the participants there. We have a third-party company, which is the origin of our data. We give them money, they give us data, right? They give us a stream of XML messages describing changes to multiple matches. And then we somehow transform this data to suit our purposes. We add some of our data from our own database, apply some of our own business rules, encode to JSON, and then we use a long polling-based HTTP push server to distribute this data to supply connected users, or rather their browsers. And once those JSONs reach the browser, we render that shiny, colorful GUI. Players pick their bets, and they return to the system with a bet, and we validate if everything is fine, and then we store it if it's all okay. Now, I'm going to focus on this transform data thing. This is kind of a curious choice. It's a seemingly unimpressive, unspectacular thing. It's a job, literally. I start it, it connects to the server, it takes the data, transforms the data, ships the data further. It has two direct clients, like these server components, but it has a lot of requirements to work as much as possible. Because if this component stops, everything stops, right? The whole feature stops, that screen is frozen, doesn't resemble reality anymore, and essentially we don't have a working feature. And because this feature plays a fairly important share in the total revenue of the business, we want it to run as much as possible. So again, you don't need to be WhatsApp to have high availability requirement. Now, also, this feature has a lot of potential for concurrency, and this was completely unobvious to me when I started implementing it. So I'm going to expand on this, right? What's happening in there, we establish a TCP connection to the third-party server, and then we receive a stream of messages. We somehow assemble, interpret those messages, and continually, incrementally maintain our own in-memory model, our own view of the world the way we want to see it. Then we usually have to store some stuff to the database, most frequently those betting odds. We strip some fields we don't need on the client side, we encode to JSON, and then send it further to the long polling-based server. Now, what you see here on this screen is literally the architecture of my initial attempt at it. So I built this thing purely sequential, single-threaded, if you will, right? So I would establish a connection, then run a loop, take the message, perform those steps, return, take more data, and repeat. And this was working surprisingly well in production for like first 5 or 10 minutes. And yeah, it would fail in all sorts of ways, which can kind of be summarized as poor efficiency and poor fault tolerance. Right, so the problem is being purely sequential. This thing is kind of like a software equivalent of a superhuman. It tries to do everything single-handedly. And if it gets stuck somewhere, which will usually be, unsurprisingly, step number 4, if it gets stuck, then everything else is on hold, right? And we waste time, and it would pretty quickly fall behind the reality, even at moderate load of messages. Now, also, its fault tolerance is very poor, right? Something goes wrong, everything goes wrong, and we really don't want it. We want this thing to run as much as possible, right? So, what really needs to happen here is I need to run different things separately. And after spending some time with Erlang, this really, to me, is concurrency, right? So I need to become concurrent. I need to run those different things separately. And there are some constraints here. Most notably, these steps, or most of them, need to be executed in this particular sequence because most of those steps produce some intermediate that is needed for the next in line. Also, I want to preserve the order of my messages, those XML messages. I want to produce my output in the same order because this determines the sequence, the timeline of events. Now, given this, the initial take is fairly straightforward. Each step is implemented as a server process, and I can establish a pipeline out of them. right? So each step will produce some kind of an intermediate. It will send it to the next in line. So if I'm a process, right, I'm waiting for the intermediate to arrive as a message. I get this message, I handle it, I do my own stuff, produce my own intermediate, send it to the next in line, and as soon as I send this message, I can immediately take more work, right? Because I'm running separately, concurrently to everyone else. So this whole thing can definitely be more efficient, right? I could still be working on the message number 1 and already starting to process and receive message number 6, while at the same time I'm preserving the order of those messages. And this is essentially improving throughput at the slight cost of latency due to the cost of this message passing. Now, this thing is still as efficient as its weakest link, which is again step number 4, storing to the database. But as it happens, at the point I want to store stuff to the database, I actually have everything ready for my user interface. So I can in fact run this thing completely concurrently to this main pipeline. And because this is of course an oversimplification of a real thing, there are some other tasks I need to do based on those incoming data, and I can do this concurrently as well. I need to read some stuff from my own database, and I can do this concurrently and then inject it to the pipeline where needed by sending a message, right? I'm relying on some third-party services, again, the same thing. And by doing all of this, I'm making this main pipeline focused on its main task, right? Which is to take the data, transform it, and ship it further. And this is, first of all, this is of course more efficient, but it's now more fault tolerant. I can tolerate all kinds of weird situations. I can tolerate database crashes, third-party services crashes, and I can still get the data and bring it to the user at near real time, right? So this will of course not be a full service because I display the data on the user interface. They come back to the system, the validation fails because we require this data to be in the database. Now even this could be worked around. We discussed some options, but legislations and other business constraints prevented us. But this is still a huge thing, right? Even when database crashes, I have some part of my service, and I will resume the full service as soon as I reconnect to the database. Now, putting this storing thing out of the pipeline does not relieve the pressure. There's still a lot of pressure, but we have to store a lot of data frequently. So it's further subdivided, right? I have different processes per different types of entities, so I can store those things concurrently. Then, especially for those betting odds, which is where the biggest pressure is, I have a separate process for explicit queuing and another process for storing those things. So I can do some funky rearrangement. I can, what I do is I batch, adaptively batch multiple items, and I go to the database with a single round trip, and I can store multiple things at once, right? This improves my efficiency. I also rearrange stuff. I prefer new stuff to old stuff. So if everything is fine, I store everything. But if something goes wrong, maybe database becomes a bit too slow for me, then I discard some stuff, and this is the old stuff, which is more probably already obsolete. And then I can do some of those interventions. It's not perfect, right? But it keeps me afloat in some problematic times. And there's a whole bag of tricks I'm using here, and again, concurrency is the main driver. But what really boosts my concurrency level is kind of acknowledging the fact that I'm dealing with multiple matches, which are, for the most part, if not completely independent things. And I can exploit this fact, and I can process matches concurrently, right? I can have like those mini pipelines per match for as long as the match is running, and then just for each incoming message, I can split it per match and forward to corresponding things. And this, of course, makes me way more concurrent, right? Just a few slides ago, I was purely sequential. And now, given that we have some 50 matches at peak times, I'm already in lower hundreds. And of course, it goes without saying that not all of these things will be always busy, right? But whatever work I have at any point in time, that work will be chunked. I will have more smaller independent chunks of work, which the VM itself can then more efficiently spread over whatever hardware is available to me. So this is more efficient, this is more scalable, and this is more fault tolerant, because a failure is now, it has less impact, right? If something goes wrong while processing a single match, it's confined there, while everything else is pushed without any interruptions. Most of my service works perfectly fine. I recover from this failure concurrently and resume the full service. And ultimately, this approach sets the stage for going fully distributed, to run things on multiple machines, have multiple machines or different machines process different matches, have some kind of a mapping rule. And because the number of simultaneous matches is the load generator here, right? The more matches I have, the more messages are coming in, the more work for me to do. This kind of, at least in theory, gives me the possibility to deal with an endless number of matches. It will, of course, break at some point, but I have at least some direction, and I'm already there, and concurrency is the driver for that thing. So, yeah, that's more or less it. If you're interested, maybe want to know more, the expanded transcript of this talk is available in the form of a 400 pages book. Yeah. There should be some discount available. I'll tweet about it soonish. And with this shameless self-plug, I'm more or less done. So yeah, thank you for your attention. Okay, do we have questions? Yes?
You just said that you cannot expand this model to infinity because it will break at some point. Could you care to explain why exactly?
Yeah, well, first of all, the Erlang cluster is fully connected. Everyone talks to everyone, so I think there is like some limited, well, what is it? It's 100 or something like that. We should hear about it when? Today? Tomorrow? Today. We should hear about it today more, but it kind of, the more you have, the more nodes you have, at some point you break. But I really think even without this property, I'm not sure how it will work, so I'm curious to hear what we have in store today. Yeah.
Is it possible to tell one node that will be shut off and propagate its work to another node, and for example, to shut down a server which is no longer needed? Or can I only say finish your work and then die, don't get new messages? Or can it also propagate the work which is doing now to some other node to do it?
Yeah, that's a good question. That's definitely, all options are possible. Now, I don't have a lot of experience with React Core, but I think it does some of this stuff, but it's kind of a guesswork. It's definitely possible, right? You have to just program around it if it's not implemented. Yeah, that goes without saying.
Anybody else?
Yeah.
What data storage are you using?
For this particular case, the database I was talking about is Microsoft SQL Server. I left the company like some year and a half ago, so I don't know at which version are they now. The interesting thing about it is that it's a legacy thing used by many different applications. So this is just like the one smallish application in the system, and many of those things are using even those same tables. There are some complex rules there, and I don't really have even quite, or didn't have a control over it, a lot of control, right? I couldn't do like what I wanted with it, especially not change it. It had to be there in that place. We have here Jim. There.
So if you were able to choose a different data storage, what would you choose?
I don't know. I'm personally a fan of SQL stuff, so I would probably go maybe Postgres or something like that. It's hard to tell. It's a very vague question. It really depends on your use case. But if I don't know anything else, I would go always for SQL.
Any more questions?
I have more practical question. What or how did you, what system did you use to monitor your application?
Yeah, that's a good question. First, in the first iteration, I had just like some tons of logs, and basically it was grep and stuff like that, and that gradually kind of went to I'm blocking. Sorry, Graphite. Yes. So we were kind of more putting some metrics and stuff to Graphite, but the main debugging tool for me was always tons of logs. Yeah, you have to log, especially when stuff is happening concurrently. This is impossible to debug. You have to log many things that are happening from many different points of view, so you can kind of reconstruct what went wrong.
And how do you distribute work between the different processes? That means, how does a single process know that this is the method that it should deal with?
Yeah, well, first of all, we are talking about this slide here, right? Yeah, so maybe I wasn't clear enough. This is science fiction, right? So this did not happen. But when it happens, basically you have multiple options. Most probably I would go for the mathematic one, which somehow you compute a hash, modulo something, and then you put it, and then you have like unique rule of no matter where the data lands, how you go there. And there are some then finesses like constant hashing, because this is of course prone to adding new nodes or removal of nodes. And then you have some other approaches to how to minimize this movability of data, so to speak. But yeah, that's kind of one approach.
But is this stuff ready in, I don't know, Erlang or some libraries, or do you have to come up with your own specific solution for this problem, for distributing the work?
Well, that's kind of a good question. So you have definitely a lot of stuff ready, right? This messaging thing, it really works no matter where it is, and because you use it a lot in your system, most of your system doesn't even care where the target is. You have some simple but very powerful support from the standard library of Erlang. I tend to use the ominous global module. It kind of has a bad name because you think that you shouldn't use it, but it has some nice support for electing a leader, so to speak, a thing that is authoritative for something in the system, right? And it works in a very chatty way. It's blocking, but for some simpler cases it works fine. Then you have libraries like millions iterations or instances of gen leader, and those kind of also can help you to elect a leader. It's not a simple problem, but it really, I don't think there's like one size fits all solution there. So you have some building blocks in place, and there are some libraries that might work for you, definitely, yeah.
Any more questions? From your experience, what was your hardest challenge during your projects?
Well, it was definitely hardest getting into this mindset, right? I came from an object-oriented perspective, and I did like a million things wrong. It's, I should do a whole talk of what I did and you shouldn't do, right? But kind of Elixir in Action is the book which is aimed to kind of guide you towards a proper place, right? So that was definitely, it took me a while to stop abusing things. I have to say I was really impressed even when I didn't really know what I was doing and did many things wrong, that even in such situations, this foundational stuff, the VM would take care for me, and some things would survive, some bizarre failures and stuff like that would still, the system would survive and keep moving on, and I would be able to see the logs and recover from them. So yeah, adapting is definitely, there is a learning curve because it's a different mindset if you're coming from an OO. It's not a rocket science, and that's my position, but it will take some time to get used to it. Yes, we have in front row.
You served the lunch today after running So you mentioned that you left the company a year and a half ago. So I presume you used Erlang for that, not Elixir, right?
No, I actually also used Elixir, but it's, in the quantity ratio, it's almost all Erlang. Some crucial parts I have rewritten in Elixir at my own spare time because I felt like it, and it actually even helped me refocus on some stuff and improve some things. But most of the things, yeah, we can say it's Erlang based.
Okay, so the second question is, how easier or harder would it be to use Elixir from the beginning?
Well, probably it depends on where you're coming from, right? So if you're coming from like an object-oriented world, especially Ruby, I would say Elixir would be easier for you. Maybe some other, especially Erlang programmers will of course enjoy it more in Erlang, right? So now these days I'm doing Erlang completely at my current company, and when I came there was a lot of code base in Erlang already, and those guys know Erlang, so it didn't make sense to insist on converting, right? So it's really a point of view. I think personally that if I were to start, I would choose Elixir because of some support I get in language and some support that I get in tools, right? But they are interchangeable and they are mixable in some way.
All right. Thank you very much.
Thank you.